Okay, we are continuing on in section 2.4. We've been talking about symmetry, and we're kind of shifting now from visually recognizing the three types of symmetry to algebraically being able to do it just from the numbers, just from the equations, rather than having something visual to look at. So this slide right here, this bottom half of page 2, you're going to want to put a big circle around this, maybe even copy it somewhere. This is basically how we're going to check for symmetry whenever we're given an equation and ask, is this graph symmetrical? Is it symmetrical with respect to x, y axis, or the origin? So with that in mind, you're going to have your notes, hopefully you printed this out. You might just keep this handy as we go through the examples that are at the top of the next page. So it says, test whether the following equations are symmetric with respect to x, y, or the origin. So we're going to use that methodology that was listed on the prior page, and I'm just going to kind of make a grid here, make it a table. So we're going to test for the x-axis symmetry, y-axis, and finally we're going to test to see if it's symmetrical about the origin. So going back to that prior page, and hopefully you have it in front of you, to test for the x-axis, it says, and we're going to do exactly what it says, replace the y with negative y. So I'm going to rewrite this equation, but I'm going to write it with a negative y instead of positive y. And then it says, if you can make that an equivalent equation. If it's an equivalent equation, what does that mean? That means that they have the same solutions. It means that you can use basic arithmetic to both sides and get back to your original equation. So let's just look at this. If we wanted to get back to this original equation, I would probably solve for y, right? If we solve for y and we ended up with x squared plus 2 on the right-hand side, we would know, yes, this is the same equation, or equivalent equation. It's the same graph. So let's multiply both sides by negative 1. Well, when we do that on this side, we have to distribute that negative 1. We get negative x squared minus 2. Is this an equivalent equation? Well, no, it's not, right? It's not going to have the same solutions. So the answer here is no. Now for y-axis, we do the opposite. We replace the x with negative x, and then we check to see if it's an equivalent equation. So let's do that. I'm going to write the equation just like it is over here, except instead of x squared, I'm going to square negative x. Okay, is there anything we can do to simplify that? It's already y equals, so it's already kind of in the same form. But let's think about if we had negative x times negative x, we're multiplying two negatives together, so those cancel each other out, and we get y equals positive x squared plus 2. And that is exactly the same equation as what we started with. So that one's a yes. Okay, this last one, if you look back at your directions, it says to check for origin. We're going to multiply both we're going to replace the x with negative x and the y with negative y. So we get negative y equals negative x squared plus 2. We already know that when we take negative x times negative x, we can replace that with x squared. And now we are to an equation that's actually the same as we had over here at the x, and we already checked. If we solve that for y, we're going to have y equals negative x squared minus 2. So that one's a no. Okay, so this first one was y-axis only, right here. Okay, second one. First, to check for the y-axis, we're going to replace the y with negative y. If I multiply both sides by negative, so that I'm solving for y, multiplying that absolute value by negative, that doesn't work, does it? Okay, let's try y equals, replacing the x with a negative x. And this one, we might not be real sure. It's inside of absolute values, so what does that mean? So let's just try plugging a number in. Let's just say x equals 5. I'm just picking a number. If this is symmetrical, if I plug x equals y into this one, I should get the same thing as if I plug x equals y into our new one. So if I plug x equals y in here, I get 5 minus 2, taking the absolute value of that. That's the absolute value of 3, or just 3. Plug it in here, negative 5 minus 2. That's going to be the absolute value of negative 7, which is 7. So clearly it doesn't work. Now that doesn't mean that if that had worked, it is definitely true. I just used an example. If for one example, I'm erasing too much now. If for one example it's not true, then it's not true. Now if it had been true, I would have had to keep thinking about it a little bit more. But if you can find an example of when it's not true, it has to be true for everything. So no. Let's try the last one. Negative y equals absolute negative x minus 2. I can divide by negative 1 to get that negative off of the y. But again, without knowing what value x is, I can't evaluate this over here. And so this is not the same thing. And again, you could start plugging some numbers in and see if there's any that is not true. So the example we just had here, y equals absolute value of x minus 2, is not symmetric in any of the 3 ways that we're talking about. Next one, negative y. Remember, for this we're replacing the y with negative y. I can divide through by the negative. And clearly that's not the same as negative absolute value of x. And you could plug a number in and see that that's not true. Okay, now we're going to check for symmetry with respect to the y-axis. What's our rule there? Is we replace the x with negative x. So that gives me y equals absolute value of negative x minus 2. Now, I don't know if x is positive or negative. So I don't know if the absolute value here is x, or if it's negative x, because if x is negative, the opposite of that would be the positive one. But in any case, if I take the absolute value of a number and its opposite, so in our original we're taking the absolute value of a number, and then in the one we just wrote we're taking the absolute value of its opposite. Both of those are going to have the same absolute value. They're going to be whichever one is the positive, that is going to be what that absolute value is. So this actually is the same. The absolute value of x is the same as the absolute value of negative x. So this one is yes. And for the last one, I replace both. And this is kind of like what we did before. We can divide through by the negative, but then we really can't, we know this is going to be a positive number. So if I take the opposite of a positive number, that's not going to be the same as taking the absolute value of a number, which has to be positive. So this right here has to be positive, whereas this one would by definition be negative. Absolute value would be a positive, but with the negative out in front would be negative. So that one is definitely not true. Okay, and the last one, replacing the y with negative y. Notice this y is being squared. That means when we replace it, whatever we replace it with, the whole thing has to be squared. And what happens when we square something that has a negative sign in front of it? Those two negatives cancel out. So we're back to y squared. So this is our first one that we've had that's symmetric with respect to the y or x-axis. For the y-axis, we replace the x with negative x. Well, that's clearly not the same. Whatever value x is, this is going to be the opposite of that. So if x was 3 on our original equation, we'd have 3 plus 36, which is 37. Here, we'd have negative 3, which is 31. So definitely not. And the last one, we replace both. Oh, so that should be an equal sign. Okay, so our negative y, we can square that and get y squared, but we still have a negative x plus 24. So this one's definitely a no. Negative x is not the same as x. Okay, let's finish this out. Just a couple more definitions. And actually, these aren't new. These are just new ways of saying something we've already said. So at the beginning of the lesson, we defined what it meant to be symmetric with respect to the y-axis. Had a whole thing up there on the first page of the notes. We are just giving a new word to that, and it is called even. So anytime you're asked, is this graph even or not, you just go back to the definition of the symmetric with respect to the y-axis. And if you look back at the previous page, at the bottom of page 2, we said if we were going to check to see if a equation is symmetric with respect to the y, we would replace the x with negative x. Do you see how this is just another way of saying that? F of x equals f of negative x. That x that's in the first one, so we're replacing x with negative x. So this is just another, it's just a new word. That's really all this page is doing, is giving us a couple new definitions. The next one is functions that are symmetric with respect to the origin. Those are called odd. So again, this is just a new definition that you do need to know. That word odd means symmetric with respect to the origin. It's kind of convenient that they both start with O, so hopefully that helps you remember it. I don't really have anything for the even going with y. There is not a term like this for symmetric with respect to the x, because these are definitions of functions. Remember on that very first page we said if it's symmetric with the x, it violates the vertical line test, so it is not a function. So we only have a word for even and one for odd. Even is y-axis, odd is origin. And this little sentence here, remember for checking origin, we replace x with negative x and y with negative y. And if we look at, this is a function notation, we're replacing the x with the opposite. So this, the way this is written, it's starting with the negative x, but the negative of that would be x. So you can see that we replace the x, and then also replace the y. F of x just represents the y value, and this negative out in front means that we are replacing the y with negative y. Okay, a couple more definitions down here. Actually, they're not definitions. These are just a couple statements to help you sort this all out. So we've defined 3 different types of symmetry. We've added a couple new definitions that apply to 2 of them whenever they're functions. And then these are just some statements that are true, that are good to know. So a function or a graph could be even and odd. It could be both. A graph, keyword here is graph. So if you just have an equation, it could be both even and odd, but if it's a function, it cannot be both. It will either be even or odd or neither. And it is totally possible for it to be neither. And that's what this very last sentence says, is a function may be neither even or odd. So a graph could be both, but a function cannot be both, but it could be neither. Okay, that concludes section 2.4.